Hello everybody and welcome to Heat Transfer. Here's an example problem we're going to be doing about the Churchill-Bernstein correlation, which is actually really easy. It's just a basic equation. But you apply it to cylinders who have an airflow going over them, and there's a possible disruption or like drag force happening, so you've got like turbulence coming out behind them. So it's just a more refined version of like fin design or anything else if you've already done cylinders in an airstream. This is just adding in the Reynolds number and those kind of values. Reynolds number and Reynolds number. And you'll see that here in just a second. So here's our layout. You can see T infinity, the velocity of the air, which is U infinity, the diameter of the cylinder, the temperature of the cylinder that's got to be at. You can read through the problem. Here are all the properties. You can use A4. Right here is TF. This is really important when you're doing flow problems where Reynolds number is involved. TF is equal to T surface plus T infinity over 2. It's just the average of the two temperatures. And whenever you have something that involves possibly turbulent or laminar flow or mixed flow conditions, you always have to use T film. You're probably used to using TS in all other problems prior to this where you just have air flowing over something. But whenever a Reynolds number is involved, you have to use T film. And then here are all the other values and constants for the specific materials that we're using. We're supposed to do it with engine oil, water, and atmospheric air. I'm just going to go ahead and do it with air because engine oil and water have the exact same process. You're just changing the values in it to these different constants. Okay, so going into this, let me get my papers arranged. So what we're going to be doing is using the Churchill-Bernstein correlation. You need to find, we're trying to find the Q flux, which is going to equal H average times the area times Ts minus T infinity. So this is the final equation that we're trying to get to because we're trying to find the heat flux per unit length. So the area here, well, Q is equal that times the area, but when you go into Q dot, you divide area by the length, which is the surface area of the cylinder, so the resulting value is going to be the circumference of the cylinder, which is h bar times pi times d, because if you divide by L all the way through, then you get Q flux times Ts minus T infinity. So this is the equation that we're going for. So we need to find h bar, which means that we have to get the Nilsson number involved. Nilsson number involved. Nilsson is kind of a weirdly pronounced name if you put the L in just the right spot. Okay, so using the average Nilsson number because we're going over the entire cylinder, this is going to equal U is equal to h bar d, which is the characteristic length. If you have I've ever done anything with Nilsson number before, you'll know that it's also HL if you're working with like a plate over K. But if you're ever working with a cylinder, it's the diameter of the cylinder is considered the characteristic length. So long as the cylinder has a cross flow like this, and the characteristic length right there, diameter. Only when it's in this situation. If you have a cylinder in a straight flow, then that's a whole different kind of a problem. Okay, and then using the Bernstein correlation, 0.3 plus 0.62 R e d to the 1/2 GR to the 1/3 all over. This is a big old long thing. 1 plus 0.4 all over PR to 2/3 to the 1/4 all times 1 plus RED all over 282.123,000. That is multiplied by 5/8, and that is multiplied by 4/5. So that is your Churchill-Bernstein correlation for Nilsson number. And we're trying to find h bar, so we're going to go ahead and move K and D over on the other side. And for air, we're going to go ahead and simplify that just a little bit more. Hang on just a second. Let me make sure I get this correct. Okay. So I'm actually going to save this moving KD over to the other side until we solve this out, just because I don't want to make it any nastier. So the first thing we got to do is we have the Reynolds number right here. So the Reynolds number is going to equal the velocity of the air times the characteristic length all over the viscosity, which we found earlier. So if you do this, you've got 5 meters per second air moving through here, and then the characteristic length is 0.01 meters, all over 16.69 times 10 to the negative 6 meters squared per second, which is equal to 2996. This is going to be our Reynolds number. Excellent. So now going into the Churchill-Bernstein, you might consider whether this is turbulent or laminar depending on the problem, but we know that we're using Churchill-Bernstein, so you can just say, okay, well I'm plugging this into here because this is the only Reynolds number that I can get. So then NUD average Milset is equal to 0.3 plus 0.62 times 2996, so 1/2 times 0.706, which is from table A4 if you have the Incompare book for heat and mass transfer, all over 1 plus 0.4 all over 0.706 to the 2/3, all to the power 1/4. And this is all multiplied by 1 plus, let me get this up here so you can see it, 2996 all over 282,000, the 5 over 8, the 4/5. And if you calculate that whole thing out, or even better, put it into MathCAD or Mathematica, and not even get your calculator involved, you end up with 28.1. So now, if you take this part of the equation, this Milset equation up here, and you move K and D over onto the other side, because we just solved for Milset, multiply by K and divide by D, you have H bar is equal to K over D times NU D average, which is equal to 0.0269 watts per meter Kelvin, which is the value of K, 0.01, characteristic length of the cylinder, which is the diameter, times 28.1, Milset number that we just solved for. If you solve that out, you end up with 75.5 watts per meter squared Kelvin. And now we're trying to find the heat flux per unit length using this equation right here. We have D, we have pi, we have T of surface, and we just found our H bar. So Q flux is equal to H bar. Actually, I'm not going to write out the equation, you just saw the equation. 75.5 watts per meter squared Kelvin, our K, times pi times 0.01 meters, which is our D, which gives us our circumference, which comes from the area, since we're doing heat flux per unit length. And then we've got 50 minus 20 degrees C. And if you calculate that all out, you'll have 71.1 watts per meter is equal to our Q flux. And that's the Churchill-Bernstein correlation. Pretty darn easy. It's just an equation and you plug in the values. The only thing you really have to look for is the Reynolds number, and then everything else just falls out of that. One quick comment here. You may notice that these units are with respect to K, and over here I have degrees C. But you'll know that the difference between, if I was to turn these into Kelvin, like add 273 and add 273 right here, when I subtract them, these 273s basically cancel back out. So the difference between degrees C and the difference in degrees Kelvin is exactly the same. So you don't have to do a unit conversion right here, but only with a difference. If it's a multiplication or anything else, anything other than an addition or a subtraction, then you have to actually do the conversion. But since here it's just a difference, no big problem. This K cancels with the C. Alrighty, and there you go. That's Churchill-Bernstein.